Hello everyone, once again, and welcome to the next segment on in situ chemical oxidation. In this segment, I'll be speaking about prognosis and outcomes from ISCO. Over the last perhaps 20 years, there have been many field applications of ISCO. There's been many performance claims made, but there is little peer-reviewed published data, surprisingly, to support these claims. Again, if you're wanting to see other information about field trials, you can stare at the EPA site cluein.org. But really, what are the expected outcomes? What are we expecting to find? What degree of cleanup are we expecting? What are the endpoints? What are the treatment endpoints? What is really happening here? Well, to answer those probing and interesting questions, I'm going to share with you today two pilot scale studies. One is a true pilot scale study in the field, and the other is a very large tank experiment in the lab. They're what I would call their extreme endpoints of a spectrum of source zone architecture. The field site itself was a well homogenized in place source zone, so it was as ideal as one could have for the way that the mass was dispersed. And the other one was a in-place pool. So as you'll see here, they sit at the ends of the spectrum. So I'll begin with the permanganate treatment of an in-place DNAPL source. So it's a long story here, but I'll begin. It's a multi-component source zone containing 1.6 kilograms of TCE and 9 kilograms of PCE. On day 0, we started to flush the in-place source with an oxidant. After 485 days of more or less sustained oxidant flushing, we stopped that. We then stopped the extraction system at day 665, and then 875 days after we started, we extracted some soil cores from the multi-component source zone. On the left-hand side is a plan view of the site. We can see the source zone. We can see 3 extraction wells and 6 injection wells. And at approximately 1 meter down gradient of the source zone, there's a multi-level sampling transect that's shown on the right hand side. So on the right hand side is a profile staring between the extraction wells and the injection wells staring upwards, and the red outline there is the source zone. So before we begin, we have a snapshot of what I would call the baseline, what was happening at the fence line. We see at that point we had a plume that sat sort of on the right-hand side of the source zone. It had a maximum TCE concentration of 142 ppm and a maximum PCE concentration of around 60 ppm. So that's the before treatment snapshot. We watched the production of chloride, and we also watched both the amount of permanganate we injected into the injection well and the average that we were extracting from the extraction well. So the upper plot is the profile for both the injected and extracted permanganates. And you can see that the over the injection period, we had a a consistent flow of oxidant between around 4 and upwards of 12 grams per liter of potassium permanganate into the source zone, and we had some residual oxidant being extracted from the extraction wells. If we stare at the chloride production below, in this particular case, we took the extracted fluid from the 3 extraction wells above ground. We did a bit of treatment on the oxides that were present. We then added some more oxidant into that fluid and then re-injected that fluid back into the 6 injection wells. So clearly we had a closed type of recycling system here. So when you stare at the chloride profile, one could conclude that for a while here, one would assume that the extracted profile should be slightly larger than the injected profile, and that's what we see if you stare at these very closely up to around day 200. You can see that by and large the extracted chloride signature is slightly higher than what we injected in. However, I would conclude that by day 300, the profiles are about the same. We have essentially extracting and injecting the same amount of chloride. Thereby, one would conclude that there is very little treatment happening. At day 478, we took a profiling tool to the site and profiled approximately 4 locations at the site. And very quickly we see a very high spike of chloride as high as close to 500 milligrams per liter of chloride. So clearly there is a production of chloride at this depth, and it's the same depth that there clearly is oxidant present. So we do have a very clear, distinct point of high chloride being produced. If we compare the before and after, you can see that the peak TCE concentration has gone down from 140 ppm to approximately 1.7 ppm, and you can see that the peak PCE concentration was cut in half. And that's the best that one could conclude from the bleb or the well mix case. The other extreme then is the extreme of a pooled DNAPL source. We have a low surface area to volume ratio, and again these form. So the goal of this work was to perform a laboratory scale experiment in this large tank to see what the endpoint would be to treat a PCE pool with permanganate. Here's the model, a stainless steel tank. The sampling ports are on the front here. We've got 3 sampling ports on the right hand side, the effluents that is here on the right. These again are the sampling ports on the front. It began by placing within the packed sand a PCE pool conducted by a post-oxidant water flush to establish a plume, an aqueous phase plume. Performed an oxidant flush. When the treatment time was over, we performed a post-treatment oxidant flush. And then step 5 was to excavate the box and take some soil cores. So here's the pre-oxidant or pre-treatment plume. It's a standard profile of a plume. One is it might expect, one is expecting, and one would predict to form off of a pool. Again, the oxidant flush and the chloride production. Again, we're staring at chloride production here because for these chlorinated compounds, they provide a very nice signature of chloride that's produced. So on this plot here, I've got along the x-axis is time, along the left y-axis is the concentration of chloride in the effluent, and along the other y-axis on the right-hand side, that's the cumulative amount of PCE oxidized based on the stoichiometry between PCE oxidized and chloride produced. And the blue line here indicates the end of the oxidant flush. So you can see that the experiment started, we had this very high peak of effluent chloride being produced, and then this long tail, and by approximately day 150 or so, we stopped the flush. And you can see even during that time that we stopped the flush, we were still able to produce oxidant, implying that there was still an ongoing oxidation process. However, we stopped the flush at that point because the pH at the interface between the PCE and the oxidant, right at that interface, the pH was less than 1. And it started to eat away at the welds in the stainless steel box. So once it was all done and we performed the post-oxidant water flush, we see a before snapshot and an after one. Note that the scales are not the same. And we see a completely depressed PCE plume, and the maximum within the PCE plume is substantially less by clearly a factor of 10. The effluent from the entire tank, beforehand it was around 20 ppm before we started to apply the oxidant. After we were done flushing with the oxidant, the rebound within the tank was around 5. Clearly we were able to impact the post-treatment PCE plume. We then took soil cores from the tank and opened up the cores and laid them out in order from left to right, or from inflow to outflow across the tank. And if you really stare at these, you can see a zone along the clay base where the pool sat, a black zone of manganese oxides that form. These are very special to the oxidant permanganate, and they precipitate at the reaction site. They start off as small colloids, but grow in size, and in the end attach to grains and become very, very hard or very cement-like. And here's a close-up on cores 3, 5, and 6. So plotted the PCE profile, the bulk PCE profile in red here as a function of the depth of the core. And the green line here is the bulk manganese concentrations as a function of depth of the core. You can see very quickly that where you get a very large hit of PCE above what one would think is the saturation level, so at that point here one could conclude that maybe NAPL is probably present there that is surrounded by manganese oxides, which will then prevent any further oxidation from happening. We now compare the field trial, the in place, the bleb trial versus the pool trial, and compare in terms of changes in mass destroyed and a change in mass flux. What we see for the field case is that when we went in and we took out cores from the in-place source, we just couldn't find any mass. So we concluded there that we were able to destroy more than 99% of that mass that was there, and the net flux was approximately a 95% reduction in the flux. In contrast, for the pool, we estimated that we were able to destroy or reduce the mass by approximately 45%, and the flux by approximately 75%. So clearly, they're not the same in the controlled experiment in the lab. One would have been hoping for a much better performance. So these should be thought as, again, as endpoints here between a bleb or an in-place source, one extreme where you have probably complete access or almost complete access to all the mass, and the pool case where you only have access to the mass sort of on the top of the pool itself. So that concludes this segment, and thanks a lot. Bye.